Our second presentation is Programmable Data Plane for Professional Media Networking, presented by Thomas Edwards, who is the Vice President of Engineering and Development at Fox Networks Engineering and Operations, where he works on advanced technology development such as UHD, OTT, and live IP production systems. Thomas has contributed to the NAB Engineering Handbook, the report of the SMPTE Study Group on Media Production System Network Architecture, and the SMPTE EBU VSF Joint Task Force on Networked Media. He holds an MSEE from the University of Maryland. He's a board member of the Streaming Video Alliance, a member of IEEE, a fellow of SMPTE, and co-chair of our program committee. Thomas?
Great. John Myatt's a tough guy to follow because not only is he a genius, he's also a tireless worker as the editor of the SMPTE 2110 standards in 32NF60. So really, everyone should give him a round of applause for all of the work he's done. Okay, I'd also like to give a quick shout out to Nick Charleglio, who is my co-author from Arista Networks, who without his aid in getting the hardware platforms and getting some of the software ported for this project could never have happened. So I come here this afternoon with a set of demands, and these are my rules. My rules are I want to control my network. I want the network to move packets the way I need it to. I want the network to not tell me what to do. I want the network to not hinder me from doing my media processing. It should help me process my media. And how are we going to do this? So this is the question that I was thinking about. And the way we can do this is by making network elements smarter and controllable. So if we go back to the early 1970s, a guy by the name of Bob Metcalf went to the University of Hawaii, where they're working on a packet radio network. They only had one channel available, one radio channel. And they had multiple sites, and they said, well, the multiple sites will just share this one channel. They'll transmit randomly, and if two of them happen to transmit at the same time, well, the packets collide, and they'll just retransmit. And that was called Aloha Net. Bob thought this was a great idea, took it back to Xerox PARC, where he said, well, instead of this being a radio network, we could actually transmit this over coaxial cable, which is kind of the same thing. In fact, this ether that we're transmitting it over, it could be telephone wires or power wiring or even microwave. And he invented what was called CSMA-CD, carrier sense multiple access with collision detection. So carrier sense means listen first, is anyone transmitting? No, then you can transmit. And while you're transmitting, if you hear someone else transmit, that's the collision detection, then you know you're in a collision, stop transmitting. And then have an exponential back off. So back off a little bit at first. If you collide again, back off a little bit more. And he was able to create Ethernet transmitting a little bit under 3 megabits per second. So this is a pretty dumb network. You basically had lines of coaxial cable, and those coaxial cables would have these vampire taps attached onto them. Devices would simply transmit using CSMA-CD. Around 1980, Intel and Xerox created the 10 megabit per second Ethernet, and this was standardized by the IEEE in 1984 as 10-base-5 with these vampire taps on RG8U. Very, very simple, very dumb network. The endpoints didn't have to do too much except for retransmit packets. So after a while, people thought, well, instead of attaching these vampire taps to coaxial cables, let's plug into these hubs, which are basically just multi-port repeaters. That made you not have to run huge amounts of coaxial cable around your office to tie into. And then someone thought, well, how all these collisions are really a problem, so let's create bridges between Ethernet segments. And they'll be smart. They will learn the addresses of the devices on the segment. And if they see a packet coming from the other segment with an address which is on the segment on the other side of the bridge, it'll let it cross the bridge. Otherwise, it won't let it cross the bridge. And this reduced the size of the collision domains, the number of endpoints which lived on a segment which could be colliding with each other, and made these networks more efficient. Then comes around 1989, came the concept of switching. So someone said, well, we have these bridges between one or two segments. What if we had lots and lots of segments? And in fact, you could get to the point where every single port on the switch goes to a single endpoint, so literally there are no collisions anymore. And that's Ethernet switching based on the media access control or MAC Ethernet destination address. Then in 1997, a couple of folks came together at Bay Networks and said, you know what, not only can we switch on the Ethernet Ethernet media access control address, but we can also switch on the layer 3 IP address, and thus was born the layer 3 switch. So now we have an even smarter switch. It switches on Ethernet, it switches on IP addresses. Fast forward to 2008, the invention of software-defined networking. Now, up until this point, switching had been done on fixed function devices. These devices have a control plane, which is generally slow, but it's programmable to some extent, and it has a data plane. A data plane is fixed function, designed to do things, a small number of capabilities at incredibly high speeds, terabits per second. So software-defined networking says, well, let's split up the control plane from the data plane. Let's have a completely programmable control plane controlling this kind of stupid data plane with simple match action rules. So for instance, we have a couple of match actions up there. We have if something comes in on port number 1, send it out of port 2. If something comes in with an IP address, destination 10.0.0.3, send it out on port 3. And if something comes in on 10.star.star.star and it has a UDP destination address of 2000, just drop that packet. So very simple match and actions. So the folks who invented OpenFlow, which was the original SDN API, recognized pretty quickly it had significant limitations. And one of them is that OpenFlow is only based on a number of limited preset headers to do that matching on. And this is a list of the original headers in the first paper. Input port, a VLAN ID, your Ethernet address, your IP address, your TCP source and destination port. You notice UDP isn't even on there, MPLS, all these other wonderful things, IPv6 wasn't even present in the first version of OpenFlow. These headers were very specific to specific protocols. So, and also the OpenFlow actions were limited to simple preset actions. Generally, it was forward a packet to a port, send that packet to a controller, or modify a field in that packet, or just drop it. There is no easy way to add a header to a packet or to try to encapsulate it, for instance, like what VXLAN does. So these folks got together and said, well, let's create a programming language for the data plane. Let's make that data plane as programmable as the control plane has been. And the concept was P4, Programming Protocol Independent Packet Processors. And this paper came out in 2014. Concept of P4 is that you can write a parser for any type of header that you'd like to define, and you can have programmable and flexible actions, kind of like writing C code for your Ethernet switch. And if you'd like to find out more about it, it's at p4.org. So the P4 model is let's separate out that control plane as before in all SDN models, but have the configuration be a P4 program that gets compiled and placed on the target switch. And then once that program is on the switch, you can then populate the switch with the various rules that you want to have in tables which cause actions to occur, which are part of your program. So in the P4 switch architecture, packets come in on the left into the ingress pipeline. You've got your flexible programmable parser, parses the headers. Those headers can then go into these flexible lookups that you program, customized actions, and then once it goes through the ingress pipeline, it goes into a traffic and managed queuing system where it figures out where that packet is going to come out of the switch. And then as it comes out of the switch, there's another egress pipeline where, again, you can have more flexible lookups and more custom actions on the packet headers. You can also insert metadata into the packet stream, and that metadata can also be part of these lookups, as well as driving some of the actions. And then at the very end, there's a deparser that reserializes all of the headers, including any encapsulation on the packet or any additional headers you'd like to add to the packet. So I thought, well, what can we do with this for professional media networking? We could, for instance, switch on an RTP timestamp, something that's not possible without programmable data plane. So imagine we've got two sources. One, it has a network destination of 239.0.0.1. One has a network destination of 239.0.0.2. Both these sources are sending SMPTE 2110-20 video uncompressed into the Ethernet switch. And there's a single output, and that single output receiver is listening on 239.0.0.3. And for a certain RTP timestamp time, I want to take source 1. For another set of times, I want it to take source 2, and then go back to source 1. And this is switching both on the destination IP address as well as the RTP timestamp that's way down in the packet header. So to use P4, you write header definitions, and it looks a lot like the C programming language. Here's an Ethernet header where we have the destination, the source address, and the ether type. Here's a UDP header with its source port and destination port, length and checksum. And here's an RTP header. So this is new to P4, right? You have all the things you expect in a RTP header, including the sequence number, if you'd like to use that, the timestamp, payload type, etc. So you use those header definitions in the parser. So we start at the top layer of the parser. It says, okay, if you have an Ethernet packet, go ahead, extract the Ethernet headers, and then based on the ether type, if it's IPv4, you're going to parse IPv4. If it's a VLAN, you can parse the VLAN. If it's PTP, you can parse the PTP. If you want to invent your own protocol, you can use an ether type that's not used by something else and make your own protocol. And then if it's something else, just go to the rest of the ingress pipeline. So if it's IPv4, we're going to extract out the IPv4 headers. And then what we're going to do here is select based on the protocol. If it's UDP, we're going to parse out the UDP. In the UDP, what we're going to do is we're going to assume it's RTP, so we'll just parse the RTP. And then here in the RTP, we're going to extract out all the RTP headers for use with our programmable match action tables. So here's our type tables and action functions. We have a table called schedule. The schedule has two reads. It reads the IPv4 destination address exactly, and it reads the RTP timestamp within a certain range of the timestamp. And this table also has actions. One's take video, if you want to take that video source, or just drop the packets. That's the other action that we have. And this is the size of the table, 16,000 entries. We can now define that action. So we actually program an action. This is a little subroutine. Here's take video. Take video with the destination IP address. We're going to modify a field of the standard metadata for egress, and we're going to say it should come out of port 1. So we're telling the packet which port to come out of. And then we're actually going to modify the IPv4 destination address to the destination IP we want it to be. And if you remember in our example, we want all of the packets which are being taken to end up on 239.0.0.3 so the receiver can pick them up. And then we've got our table. So we populate the table and we say for 239.0.0.1 input for certain RTP timestamps, take that video and give it the right destination IP address. And then for 239.0.0.2 for another range of RTP timestamps, take that video and then go back to source 1 here, 239.0.0.1 for another range, take that video. And if it doesn't fall into one of these categories, the default is just to drop those packets if we're not actually selecting those packets. So we can simulate this in software using software available from the p4.org site. Using the P4 behavioral model version 2 simple switch target. So once we write our P4 program, we compile it, and it creates a command line interpreter to the BMV2 using the Apache Thrift remote procedure calls. And we can come in and we can set up our tables, and we can add our schedule, of, with the IP address, the RTP timestamp range we want, and the destination IP address. And then we can use SCAPI, which is a neat way of generating packets in software to generate RTP packets and send it into the simulator to test this out. And you see on the bottom, we've got a source coming from 10.10.10.11 and a source coming from 10.10.10.12. And you can see it's taking this first source from time 1 and time 2. And then from time 3 and time 4, it takes the second source. And then time 5 and time 6, it's taking the first source again. So here we are simulating switching RTP based on RTP timestamp. So SMPTE 2110-20 has a neat property that the entire frame carries the same timestamp. So we can set up an actual proof of concept. And if you'd like to see this, it's running in the Arista booth out in the exhibit hall, where we have a live camera, we have an SSD video source. The two go into a Devion card where it's being turned into SMPTE 2110-20 RTP. The combined flows go into this Arista 7160 switch, which is a switch that has the Cavium Expliant network controller on it. It does the time-based switch, the RTP timestamp-based switching. The output comes out, it's decoded, and you can see it on a screen. The way we've taken the P4 program, and Arista has generated ported this basically the C code for the Expliant processor, which is on board the Arista switch. So it's implemented as a value and a bit mask. So basically in this POC we have in the exhibit hall, it's switching back and forth between the live video and the video off the solid state player approximately once every 5 seconds. And we have a very simple Python program running on the switch, which allows us to place the schedule for the switching onto the switch. So this is one example of something you can do with programmable data plane by using the RTP timestamp as part of your switching decision. And by the way, it works. We actually captured packets. Again, here's the second source at .12. And then right here, it's switching over to the first source at .11. And you can see this is happening at the last packet comes in, starts at line 719. And then the first packet of the next frame starts at line 0. And of course, the RTP marker bit is set true to the last packet in the frame. And this is the first packet in the next frame. So it's doing frame accurate switching of SMPTE 2110-20. So something else we can do with this is Multilink RTP. If you like to carry RTP over multiple links, you think, well, there are lots of ways to do this in the world of Ethernet networking. I've got port channel or link aggregation, also known as lag, or equal cost multipath at the IP layer, known as ECMP. Unfortunately, most of these solutions are based on what's called the 5-tuple header, which basically only extends out through the Ethernet IP and maybe the TCP or UDP port numbers. And in your RTP packet, which is, those are going to be the same for every single packet in your flow, will have the same 5-tuple, so they'll all hash to the same output port. So the problem is you can't actually spread an RTP flow across multiple output links using the standard mechanisms available to you with switches. But we have programmable data plane, and we can now tell that data plane, well, instead of hashing on the regular 5-tuple, hash on the RTP sequence number, as well as the destination IP address. This allows us to be able to take a single flow in, have it spread evenly across a leaf spine network, and then it can combine back in and go out like that. So we're able to simulate this as well. This is an example of a single flow, which is coming in, and this is the output of the switch. And you can see sometimes it comes out of port 1, and sometimes out of port 2, and sometimes out of port 0. So again, we're hashing based on the RTP sequence number. Something else we can do with programmable data plane is the ability to do lower thirds on an Ethernet switch. And what we do now is we can reach all the way into the SMPTE 2110-20 sample row data headers. So the header definitions are over here. So we'll look at the SRD row number, and we're just picking off the first sample row data header in the packet, and make a switching decision based on that sample row data, sample raster data row number. So here's a simulation of the same thing. We've got multiple packets coming in. Here's the first source is .11. The second source is .12. The switch point is right here. And the switch point happens, the last packet here is coming in on line 480. And the next packet starts on line 481. So we're switching about 2/3 of the way through the frame, switching from one source to another source. So in conclusion, the history of network switching is really one which has been evolving from dumb networks to smarter networks. And while software-defined networking really brings us incredible programmatic and precise control of networking, it's limited in some ways, and programmable data plane makes that packet processing more flexible. And professional network media can use a combination of SDN and programmable data plane to perform media-aware packet processing. And we've been able to show these examples not only in software simulations, but also in real-world proof of concepts. So if you'd like to take a look at some of the P4 examples, which I have discussed in this talk, they're all available on GitHub, github.com at Fox Neo Advanced Technology. And thank you. Mr. Kovalik.
Yes, indeed. Nicely done, Thomas. A couple of questions. How deep can you go with regard to P4 if before the Cavium processor won't be able to do it?
That's a good question. And it's going to be network processor dependent, right? If you have a barefoot Tofino chip, it'll probably be one answer. If it's a Cavium expliant, it'll probably be another answer. So it is a bit network dependent. Certainly you can do a lot of, I think you can do a lot of interesting things without too many stages.
You found a limit on using the Cavium example?
Well, I say, so the only thing we've done with the Cavium in real-world POC is the RTP switching. So it certainly can at least do that. Things like the RTP, Multilink, and the lower thirds we've not actually done in hardware yet. We've only done simulation.
Of the off-the-shelf switches, are any of them open towards this, or do manufacturers say, no, you can't do that? You had some help with Arista.
This is a question the networking industry is grappling with, is how much of this programmability to expose to end users. And I think there are two different camps. I think there is one camp that says, yes, everybody should be able to learn P4 and everybody should be able to program their switches the way they wanted to. There's another camp that says, well, maybe you have specific applications within your industry and we, the network vendor, will write the code kind of for you and we will make sure it works well and we will support it and we will place it on the switch. So I think those are the two camps right now, and it's still a new enough concept that there's not been a real final decision in the marketplace.
Any other questions for Thomas?
Okay.